Hello, Assalamualaikum. Today, me and my friends are going to solve on tutorial question 3 of example 8.1 in the 5th edition of Fogler's textbook. From the question, reactant A decomposes by 3 simultaneous reactions to form 3 products, one that is desired B and 2 that are undesired X and Y. In the question, the rate of disappearance of each equation are given, and also the temperature and the activation energy of each equations of E1, E2, and E3. Question A asks how and under what condition reactor types, temperature, concentration should reaction be carried out to maximize the selectivity of species B for an entering concentration of species A of 0.4 molarity and a volumetric flow rate of 2 dm³ per second. And question B asks how could the conversion of B be increased and still keep selectivity relatively high? The first step is we need to calculate the selectivity, and this is the general equation of selectivity, and this is the equation of selectivity with respect to B, where the B is the desired product and X and Y is the undesired product. So this is the final equation where K2 times Ca divided by K1 plus K3 times Ca the power of 2. Then from this equation, we need to plot the graph of selectivity versus concentration of A. So here is the graph of selectivity versus concentration A, and where the concentration A, we put the range of 0 to 0.5 to get the respective selectivity value, and it can be seen at concentration A star is where the selectivity is at the maximum point. In order to find the maximum value of selectivity, first we need to know the concentration of A star value. So in order to do that, we need to differentiate the selectivity with respect to concentration A and set the derivative to 0 to solve the Ca star. So by using your calculus knowledge, this is how you get the equation, and solving for the Ca star, this is the final equation, which is the square root of K1 over K3. And from the question, the value of K1 and K3 are given. So the value of K1 is 0.001 mole per dm³ dot s, and the value of K3 is 0.008 dm³ per mole dot s. And the final answer is 0.112 mole per dm³. So at concentration of 0.112 mole per dm³ is when the selectivity value is at the maximum point. After calculating the value of Ca star, then we can calculate the value of selectivity. And this is the equation of selectivity, which is K2 times Ca divided by K1 plus K3 times Ca the power of 2. So we will substitute the Ca value with the square root of K1 over K3, and then after simplifying the equation, we will get K2 over 2 square root of K1 times K3. And as I mentioned before, the value of K1, K2, and K3 are given in the question. So after substituting the value of K1, K2, and K3 into the equation, we will get the value of selectivity is 0.84. After that, we need to calculate the volume of CSTR when the exit concentration is at Ca star. The net rate of formation of A from reaction 1, 2, and 3 is as below. Negative Ra equals to K1A plus K2A times Ca plus K3A times Ca the power of 2, where the CSTR for this liquid phase reaction is at constant volume. And this is the equation of CSTR volume, where the value of initial volumetric flow rate as well as Ca0 and K1, K2, K3 are given in the question, and the value of Ca star we have calculated before. So substituting all the value we get, we will get the volume is 1566 dm cube. In conclusion, for an entering volumetric flow rate of 2 dm cube per second, we must have a CSTR volume of 1566 dm cube to maximize the selectivity. And to maximize the selectivity with respect to temperature, we can use this equation. But first, we need to know if our selectivity with respect to temperature obeys case 1 or case 2. So for case 1, if the E1 plus E3 divided by 2 is less than E2, it runs at as high temperature as possible with existing equipment, and we need to watch out for other side reaction that might occur at high temperature. And for case 2, if the E1 plus E3 divided by 2 is more than E2, it runs at low temperature but not so low that a significant conversion is not achieved. So for the activation energy given in this example, we need to calculate either our equation obeys case 1 or case 2. So E1 plus E3 divided by 2 minus E2, we will get the value of 0, which does not obey any of the cases. Hence, the selectivity for this combination of activation energy is independent of temperature. Then we can calculate the conversion of A in the CSTR with the equation of X equals to Ca0 minus Ca star over Ca0, which will get the conversion value of 0.72 at CSTR.
Next is how to increase the conversion with height selectivity. So the conversion in CSTR calculated, which is 0.72, is based on the equation below. So as shown in the CSTR PFR arrangement figure, the inlet stream of PFR is based on the conditions of the exit stream of CSTR. The conditions are: first, the conversion is 0.72. Second, the concentration of A is 0.112 mol per dm cube. Third, the selectivity is 0.84. Based on the conditions before, let's say the conversion is to increase from 0.72 to 0.9. So along the length of the PFR, the concentration A is changing as it moves down the PFR. Based on the selectivity and concentration trajectories, it shows that concentration A is decreasing as well as the selectivity inside the PFR reactor. So the decreasing concentration of A has increased the conversion. This is because the remaining of the concentration A is reacted to produce the desired product. Thus, the conversion is able to achieve at 0.9 conversion by adding the PFR after the CSTR and find the selectivity is being decreased.
Assalamualaikum. My name is Shafika Amira. Today, I would like to propose a reactor scheme to achieve maximum selectivity. So, which reactor can be used to maximize the selectivity? We need to use reactors that can operate at a given concentration. PFR cannot be used because the concentration is varied at the entrance concentration. As we can see from the figure 1, selectivity as a function of the concentration of A, 0.4 to lower concentration is not operating at the optimum concentration. So CXTR is much more suitable to operate at a given concentration. So what we need to do if we want to achieve a higher conversion, we need a second reactor. So if we use CSTR, the concentration will not operating at the optimum concentration, so selectivity will not achieve the selectivity and the concentration will not achieve the maximum level. We opt for PFR as the concentration start at a higher concentration and then it will gradually decreasing the selectivity and also the concentration. Thus, more desired product B can be produced and formed. So figure 2 shows the CSTR and PFR reactor arrangement.
Okay, lastly, the last slide, the chemical profile of concentration of reactant product in the PFR, the maximum selectivity and conversion value of inlet stream, originating from outlet of the first reactor, which is CSTR. Okay, let's take a look at the graph. Based on the graph, it shows that when the product entering the PFR from the CSTR, it shows that concentration of reactant A being decreased while the other product increase. The other product is B, product X and product Y. Product B is higher compared to the product X and Y because product B is the desired product for this process. The graph also shown that along the line in PFR, the conversion increased with the increase of the space-time. In the conclusion, this proved that the concentration of A decreased with increasing of the conversion. The selectivity in PFR decreased with the increase of conversion. That's all for us. From us, thank you.